basically, guys, practical reasoning, rational reasoning. So what's the logic? So basically, it's like something in question. You don't have in a perfect world. There's no questions. There's no questions. Because everything has already answer, defined answer. Rigid answer. So we're taking like, why am I having this problem? Why does a problem is happening? For example, if I have a condition in the sea, in the ocean, I'm ocean coming down, transcending to my ocean. From my air, I live in the ocean. And in the ocean, I'm literally in the ocean. But my sonar started. I can either go to my boat and get consensus. But if it's my ship, my crib, where I live, where I stay, my ocean, I don't really ask no one. I never ask no one. So I can go there and never ask no one for my ocean because that's my item, because all the consensus, all the thing I own, it's mine, me, myself, and I. It's bound to me. If it breaks, I rebuild it. Rebuild it, repair it, renew it. It doesn't matter who the relationship is. It's my own. I do anything I like with it. No, honestly, when you own something, you delegate it. And that person owns it forever. But delegations can basically basically. So basically, I got third council. Basically, the talk was upset. No, this is something else. Let's transfer it. Oh, I don't have the link. Oh no. So basically, I just need to get this up. So basically, I'll get up last because I didn't plan for this. So basically, I have to get my video from Substack, Hamiltonian Elimination, via Keystone Problem. OBINexus, upload github.com/OBINexus to Keystone Problem to GitHub OBINexus repository for this update. So I want you guys to do this small called a Cisco packet. Risk is a small set of ships. Basically, this is a risk architecture. We have CISC, but the problem with this, risk is completion. Oh wait, stop doing this nonsense. My computer is annoying me. So basically, I'm trying to make my computer understand that risk SS and there's just different one models to do it. So basically, they polarize together. So when some information is risk comes in, it knows it's 6, and 6 does basically northeast pole problem for data transmission. So this is a control piece, but basically like this is nothing. This is basically I'm trying to get the poles align the data path. The way align, but the IR is the problem. The interpolation problem, what do I call it? Intermediate representation of the whatever being processed in memory. Basically, I'm trying to show that I want to build my assembly language. It's like a MMUKO assembly language, mmuko-os. What should I call it? The mmuko assembly. I'll come up with a good name, but I want to make a rift. A rift is a focus transform. Rift mmuko assembly, something like that. But it's bound by the Cisco model because Cisco's consciousness, it just does it. So basically, anything that's at a log that's bound to 01 scale happens in login time. At the best case, in the worst case, at rest. So basically, any instruction that runs in parallel at the concurrent level, in the concurrent level, in parallel, in the shared data model, via a Cisco packet in this world. I'll come back to Cisco packet. Via a Cisco and Cisco packets share the same plane of existence, which is like the data stream, the send receive signal, and that's like a packet system. So this is very important thing to formalize today. I'll go halfway through the formalization, but I don't want to ruin it for you guys. So let's do it properly. So we got this model. So basically, you get information generate post. So you get some. So basically, you don't understand this. Yes. So basically, you get A start, A and A. But A start and A end have a matrix of 4. 4. The share of one which is start and end, which is 4. So when A start is B epsilon. So A start is B epsilon. So B cannot see A. B and end. B start is A's end. So B knows end. I don't know when they end. So come to my end start. So don't come to my end. So A start is just a because it's a minimum start, maximum start. You can have 2 poles. So okay, I can go only positive because they share one space area. So plus plus minus minus, but they are sharing one degree, and that's polar coincidence. So this is a model here. So as you can see, A star is big, but these are branches. So the problem with this is you kind of have this unvariant branches because you have to give people consensus over you don't know. If you here after your branch need consensus automatically, they need consensus. That's the problem. So if they get A star, the problem is these branches are not giving them the area here. So when it goes out bound, you have to use pi. So you have to show basically A start, So you get A start n. So A start n is here, middle 90 degrees, no of B. And then A and n is the second one. Basically north one of B is the x-axis. Because so basically, I'm trying to give you the encoding table actually. So the encoding table for this is what's my pen? So what's my encoding table? My encoding table is I can do the proof actually. A 0 0 A 0 0 A 0 0 is B E E E E 0 1 0 1 that's B E 1 X 1 1 0 1 E E 1 1 A 1 0 is B 1 E E 0. No, listen, I'm trying to give you now. So we get 0 0 we get 0 0 and then we get without the tracking, no tracking. No, all this resolving. Resolving scene, so we get this is just I'm gonna do it now actually. A 1 1 1 1. This is B 1 1 1 1. So basically, because A starts okay, so here we get so if you don't understand, A start and it's 1 1 1, all share space 1 1 1. And they get a B start, A start, so where A start and end 1 0 1 1, that's the Y end, so it can be 1 1 and 1 0. So when A end is 1 0 1 1 1 0 1 0 1 0 1 0, so you get 1 1 0 1 0 1 0 1 1. This is just a encoding of it. So you get the step 1 0 1 1. So you get this. So you get 1 0 an X and Y. So you get the conjugate one. So when you get one, you get so if I have some information, very important. If I'm trying to create a table, a protocol, 1 0 or 1 0, I send a 1 0. I can send 1 0. I can send 1 and some pause. So the pause is epsilon in A. But that's nothing, no information. So why this really matters, how this really works is this. So say I want to send some Schumann bytes using my table, send some message, how do I send create a session, a micro channel. So create a session and then send. So create, read, update, delete. So so I create a session, create, read, read. So I get 2 channels. So we share one channel. Update, delete. So if I create it, I need if A wants to come into B, A has the same space. So A doesn't want to waste any time. So A wants to assign epsilon. But what would he send? What does that mean? He says nothing. How can you say nothing? Nothing. You can't say nothing. You do nothing. When you can't say nothing, you do nothing. That's what the concept is doing. You do nothing. So, but what does that mean? Now, so let me show you the table. So, epsilon equals D do nothing. E, so you get E, O, you get for a table. So you get table A is EE. You get if I can create a session, epsilon station, I can read it. So I can read the session. So I have read, create, and then read. So E will become E R. E will become R because XO O EE will become O R, or EE will become R read. So that'll be in read mode. So it'll be read mode. So this will be read mode. But read mode will be a state. A state in a session state. So a temporary session, that's like a 5 minutes read. I want a 5 minutes function. So read mode, 5 minutes read. So reading for 5 minutes. Then I want to write. So create read update. So this will be write execute. Write or execute on write. Because write will be saving. So anyway, so or temporary saving, which is save. Okay. 0 0 epsilon. So when I want to write, I take the state XO, and that XO will be exclusive O, and that will be what I want to always store is something in the pole or XO. So O 0 0 is 0. Now O exclusive O 1 0. So this is so just 0. So my computer just give me 0. Everyone shared 0. So in the state of reading, I just get everyone's state because that's the state. That's what we all share, you know, between A and B, A to B. So get 0 0. Now get updates. Read. Read. So write. If I want to write this, I have to. I don't guess. I just do it. So I write it. So for me to write it, I'm thinking about epsilon solution. Epsilon, just nothing we all share. Nothing we all share. So if I want to write an epsilon to this, I just save it. But you know, I only need one save, and because I've only need one save minimum, I don't have to write it again. I don't have to save. I just like this is basically I'm creating a channel, so I never have to write again. So the channel just stays. So this only makes sure I need the 2 by 2 matrix. Only 2 epsilon matrix, 2 by 2 matrix. I need to store 0 and a read operation of 0 and 1. Now, so to store your bytes, 8 bits, your bytes, you know, basically my computer we have 8 bytes, but in your bytes is 8 bits, so I'm using your computer's logic. So we destroy. So for me to destroy the session, I then have to reset everything to epsilon. So that's the idea here. So this model allows you to set. So when I send this, I'm doing the same thing for your access. So now, we are back to epsilon. So create I read something. I read to your desk. So your one is to read something. I create something. To create something is like all epsilon states or 0 for you anyway. So I never need to store it. So create update. So basically because it's already epsilon, you just have to make sure that your nothing is time bound, because you know basically if this is a space I store it, you know that you can have to compute that space. What does it mean to store epsilon? So or allocate the buffers. Cool. So you're trying to organize in my computer. I'm trying to have 8 epsilon bytes, and that will be 8 0, and that will be that will be 0 to the power of 8, and that will be 0 to the power of 8 in the standard notation, and 0 to the power of negative 8 bytes in your notation. In my notation, because you know, in my notation, 8 bytes would be like the floating point position. But for human rights claims, 8 times 8 is 16, 64. 64 plus 16, 18. No, 64 plus 18 is 80. 80 bytes. Reserved. The computer has reserved the memory. 80 bytes reserved. You know, not bits, 80 bytes. Sorry, 80 bits reserved. So, because we're going to go bytes. 80 bytes reserved. We'll share 80 bytes. You know, so we share minimum, and maximum. We'll double this for this to work. 80 bytes. So if you want to share a byte with me, 80 bytes is the minimum I give for you, your private world. You know, and I give another 80 bytes maximum. So we share a total of 160 bytes of data for you to send me a message in MMUKO system. So the proof is really because of the system implementation. For example, when you read the system, when you basically your time to compute this, your space you need to store this, is my time to compute it. That's what it is. Your space to store it. So, for example, if you're storing this in log n, instant time. So my one is all constant time, or one I already know, you know. So basically, your space is in your time, in your time, in your time. The space and time in your personal time is basically you're using as you're using space. You cannot use the invariant time because we're living in space time realm. You cannot even touch some of the time because we unless you can't touch time physically, but you can't interact with time while it's processing. You have to sacrifice something. You have to sacrifice your full space, or the space you're in, whether the box I'm in, or your full time, So pi r squared, the area, or 2 pi r VMI's model. So basically that's the idea there. So this is just a coding table. A start and end. A start A start because the 4 starts for end and end. End. A start end. A start end. A B start end. B start end. A start A and end. A and end. B and end. B and end. And because it's just a 2D model, but then if you have a tree, you have 3 more inputs you have to do because it's 3D world. First you have to get all the coordinates polarized. No matter the model, no matter the data it's whether you have a constant time or you have it to reference show or alias, it's not really the problem. But the alias is in trapper alias. So the idea is you have the Cisco packet. What is Cisco packet? The Cisco packet is what I really want to give you. So you have the standard model. So I want to send a bit of information. So you want to send to me in your epsilon world. In our epsilon world, we don't share anything. 1 1 0 1 0 1 1 2 3 4 5 6. I want to make the word hello world, hello mmuko-os, hello welcome. Let's do welcome, welcome. Let me find that in bytes. 1 second, guys. Basically, should be like a welcome in bytes, in bits. Welcome, world, welcome. ASCII bits, ASCII table, calculator. Welcome. So this hex dump basically for welcome OBINexus. So the number that converts into the binary of so basically if I want to type in welcome in decimal, we will share decimal state of like a caniconicolizatoon, fractional caniconicolizatoon, like a fraction. So basically, if I want to convert welcome, OBINexus, full stop, dot, because it's kind of loading. Obviously, welcome OBINexus. I'll put 0 1. The word welcome will be 0 1, 0 1 0 1 1 1 0 1 1. Basically, you get. Let me just put the word welcome because I don't want to fuck it up. So you get W is 0 1 0 1 0 1 1 0 1 1 0 1 0 1 0 1. But let me just put W actually because well 0 1 0 1 1 0 1. So the word W is 0. See, W is binary 0 1 0 1 0 1 1. That's W. E is letter E is 0 1 1 0 0 0 1. Basically that's E, and then we'll put L double L W L. Basically I'll put the word well instead of welcome. So that'll be well will be 0 1 1 0 1 1 0 0. And that'll be so this is L times 2, so we get 2 L's. Basically, so this is not fucking me up. Can I see myself? So I'm gonna give you the solution to all of this via Cisco. This you have to get more paper before I do it. I'll fuck it up if I mess my proofs off. So I'm trying to prove something to you right now. I know it works, but I want to prove it works with my own framework, not what it says. So this works because of the poles. So we get the data packets there. I don't know, I just fucked up myself. basically we got that. W in ASCII is research here. So let me prove this works. So how this works? So each stream of data is canonical. I can have the row or column. So I have to get the row and column aligned. So 0 in the row means 0 in the columns. There's no if but, because a row equals a column. The structure is the meaning. Structure is a final syntax in rift. You know, when you are flexible, when you're putting yourself. So what this means is we have a shared contract via interpretation too, depending on whatever interpretation was meant to be agreed on in our realities. Okay, so we get 0, 1, 1. So what would this mean? So x source state. So we get the so a times b. We share a to okay a times the ad is what a and d. So my start is your n. My start is your n, and that's basically my 0 is your epsilon. So your epsilon, so e times 0 equals ad, and that will be epsilon state canonical. And then we get e times epsilon. So basically e epsilon start and then 0 times e equals d. So you get d1, d1, d2, which is d, which is each of the e, or what shares the 0 is. And then we get the 1. So the 1 for me to have the 1, I have 1. So this is the 1. The 1 will be space time. So the secret space time, the 1 will be 1 times 0 will equal to 1. 1 times 1 equal to 0, 1. So we get 0, 1, and we get 1 times 0 equals to 1, and then we get 0 times 1, or e, which was XOR, and we get e, 0 times 1, 0 times 1, that's 1 or 0 equals 1. And you get a full 1. This would be 0 or 1. This would be the row 0 or 1, and you get a column 0, 1. So basically, the idea is you get the 0 here, and you get this one. You get the matrix, but you see like this here. You get here. You get epsilon, you get 0, 0, 1, 1, 1, 1, 0. Basically, you get a matrix. Basically, determinant matrix, just like over the matrix. So if you want the fractional form, you do 1 over the matrix, like the unit, you all share. The half. So if you have the unit 1, you have the half of the unit. So the unit we all share in the fractional form is a conjugate inverse. So you do 1 over the matrix. You will have 1 over the determinant matrix, and this will give you the fraction you share. So we share 4 fractions. 4 fractions. That would be tens, units, 10 units, half a fraction, unit dot tens, and then hundreds. So in my reality, we get tens. We get the tens, so we get the unit model. So we get fractional, basically unit modeling. So my unit 1 half, 1 has a half, minus a half. Basically minus a half and half and minus a half, plus minus a half are the same thing for the same plus half. If I want a negative fraction or positive fraction. So basically if I do 1 over some 10 over 10, I have that's basically times. If I do times 10, I get 1, the full 1 back, the full whole data, so sure. I'm not doing a model back, and vice versa. But if I do 10 over 1 over 10, 10 over 1 times 1 over 10. 10 times 10 is 10. Times 1 over 10. So I get 11. So basically 10 times 10 is 10. 10 times 1 is basically this is 10. But if I then add it, if then add the unit of 1 to 1, which because I already have it before I go negative. If I have the half unit of 1, which is over 1 over 10, I get that 2 halves into the 1, and that's 10 plus 10, which is 10 and a half. I mean 1 and 1 whole and a half. Basically 1 whole is basically, if I have 1 whole and a half minimum for my unity, and another half for yours. That'll be 11. So we all share 11 states. And then if you wanna, we can accent to it. If it does this, so what I'm saying, it's meant to be there. So you get A star and A in there. Via the same so the computation over the space that is sparse is the same thing. Via configuration. So the configuration is just basically me moving my eyes active. So anytime I do, basically there's no difference between space and time. They're just half of the same thing, because space needs time, time needs space, space time. You know, but which one is first? For them to both agree, there's just consensus for us to breathe. That's what we want life. You know, this one just has space and time. Just it doesn't follow itself. Listen. So I'm seeing that we share 11 dimension, 11 over 11, which is 1 unit, and we with 1 unit, maximum. Local, let's call it local minimum, local maximum for each individual person in life. But we have 10, we have 1 full unit of a 10 over 10. If 10 is the maximum dimension you can enter, if basically in 3 dimension you can enter. So basically, say the example, so we double, say we have a force, we double the force. The force is double. Say we have the force to go tell this room. So we get 7 feet of area. 7 times 7 is this area. We get 49, and then 7 plus 7 is what? 14. So its area cubed is 3, 9, 10, 11, 12, 13, 14, 9, 10, 11, 12, 13, 63, 4, 5, 63 union. So we share this space 63 squared. Now we share this space 63 squared. Now this is just my area. If I want to give you what I don't know about my area, I can give you that by just flipping my dimension 1 over 63, and you can see this. You can see this. You know, because I just send it to you. You know, that's the idea here. So when I send the information, the Cisco packet submitter literally just give me the information I send before I open it. Because you know, I don't have to open any thing I can't see. So you can't harm me. It's a virus code, so I can see what the code contains, what it before execute. So it's basically 1 over execution. So let's go here. So everything I have 1 over read, 1 over write. I see it. I can see it because I can track it. I can track it. I can telemize it. I can view the artifact. I can preview it like a PDF or some kind of model and send it over a network. You know, that's what Cisco really is. So I'm gonna start this video without completing the proof because I think I get kind of buggy. But you know, this idea, the Cisco proof allow you literally to send something that you can never tamper with. You know, you can never tamper because you know it blows loads of physics. And those boxes ever again, guys, you lose all your work. You know, that's the idea of Cisco. So Cisco works by the poles. So let me just give you so if it's basically how it works. So you go see if two people can read. So read, write, execute. Execute in this context is send. So if I write some bytes, so read, write. So if I have like a one write, if one person send me a read something and send it to me, that's one read, sends to me. And I make the virus complete, and I send it and I write it down. So we both, so I have, say like the worst case, we both share a state. So me and MMUKO will send it. So we have 1 read, 2 writes. So basically, I'm trying to compute 1 read over 2 writes. Safe, no execute needed here. Pre-fight flash, basically, no pre-fight. You can't execute it. You can never execute because the pre-fight execution removed. That's the thing. It doesn't think about the policy. So read and 2 writes. So the SQ needs an extra flag or extra encoding. So I just don't track the state. I just ignore it. And that never comes to me. So execute is gone. So I'm trying to compute 1 over 2RW as the previous state. You know, no it's an image or something. I can't execute. No executing. You know, so the read, write, execute. So read dot write. So how would I do this? This thing you know people to do it. So this is good. So when I write, I can read to read. When I read, I can read, and I have a little read. But I cannot execute it if I see it, if I know what it is. If it's public, oh my days, nowadays. So basically, how does this score packet work? So basically, I get the conjugated matrix. So I get the letter W. I'm trying to preview W, never to see it. I never be scared of this encoding because so advanced, so it's so advanced it doesn't break. 1 0 1 1 0 1 1 0 0. So I get 0 1 1 in a row. I get the conjugate row, the conjugate form of the row, which is the so I get the matrix 0 1 0 1 and then 1 0. This is a 2 by 2 matrix. And then we get the other matrix 1 0 and then 1 1 1 0 0 0. Those are two matrices I get to send. So for me to come with the conjugate of this matrix, I do my one is 0 times 0 equals epsilon. So and then 1 times 1 equals 1. So I get 1 in this one. So E1 is what I see. I store E1. And then I try to remove the 1, so because it's like, and then I get 1 0, 1 times 1. So in the other matrix for the welcome, 1 times 1 is 1, and 1 times 0 is epsilon. So I get E1 1e. Basically, the formation is not complete to execute. So I get 1e, I get this function, but I then have to think about the execute coding. So when I send it, I don't want anyone to see it. So see what I send. So I just send it. So basically, it's like content machine virus. So you can basically how does this work? What's this? Okay, what's this now? So how does this work? So this is so I get this matrix. So I get e for epsilon. 1 and then 1e. That's my buffer. That's what I'm sent. So that's really what I sent. What I sent, but they can see. So for me to get it, I can. So basically, I get 1 over e1, 1e. So this one basically it doesn't hurt me here. Because I'm so this stage is what I'm trying to get. From the core end. So get it. So if I execute some of this virus, I get the send. So I just send it. This and after send. So and then now add x. X is another SQ, so this can be a 1 more byte of read write SQ. So I get a 1 or 0. So I get 1 or 0, 0 and 1, or based on the endings, which is the left shift, right shift, R matching, and we get the homogeneous, heterogeneous endings. This is a homogeneous send. And this is a heterogeneous send. So 1 0, 1 if sent. So this is sent, but I can't verify it. Can't fully verify send as a partial send. So you get sent. So get sent. So you get 1 1 1 1. So this is all sent. So we're trying to define the a bit of the so. We're just trying this fully sent state of 1 1 to really see 1 1, which represents obviously the 1 full and into the x. So we're trying to define uniform 1 1. So 1 1 1 or 1. So it never execute. So 1 over 1. So we can just prove the 1 over 1 on 1 because that's the conjugate determinant matrix over the vector field because we don't need the full vector space. So how does this work in Cisco packet? So you're gonna define some kind of function. You don't define anything. You just trace the system. So people say you diagram. You do extend. So you do extra operations already on it. So basically the state of this extra operation is this. So XOR 0. So when it's sent, the full information is 1 or epsilon or 0. 0, I'm doing this 1 0 1 e 0 and then 1 1 0 0. So you get this is you get e. So we share a new system. Well, once you get into just the new state, 0%. So we can only preview. We don't even have to open the email. So this is email stuck in preview thumbnail mode. So we get 0 1 e1 0 e is 0 e is 0. So we get when we see a 0 e 0 we put on e. I want epsilon as well. So when we see a 0, then we get we get 0 0. for all states. That's the goal. So we get 0, E will be 0 0, and then 1 0 will be 1E, and then 1E will be E1 will be 1E, 1EE, or epsilon, which is 0. We can send back and forth via this. So we get 1 1 will be 0 1. So E E1. So this is the matrix. So we get 1E, EE, E1, XOR, and then we get exclusive OR, and we get the opposite one, which is the 2 by 2. So EE 1 1, and then we get 1E E1, and we get the inverse matrix. We get 1. Should I copy 1 over E1 and 1E, and this is a matrix. So E times 1 is 1. So 1 if you can execute it, and E if you can't execute. So the data packet E, we have to store E, and E is hard, like, because we must say something. E is, we get E, we get the poles E to E, A. So we get AD times BC, in the state AD times BC, as a message to preview. But we can basically, when we ever preview this, we never have to open that image. We can see everything, we can action everything, track all the state, see what's going on in the messages, and never actively pursue the because the thing will store. So one thing to use, we just replace 0 with an E, but with diagram. So 0 is an E, 1 is a 1. What's it? 0 is a 0. I'm not really done here. 1 is a 1. 1 is a 0. 0 is a 1 is a 0 is a epsilon. 1 is a 1. 1 is a 1, and 0 is a 0, and E is an E. So basically, we just raise up. But there's one more problem. So this is a problem of sending by structure, not syntax. So what Cisco does, what I could do is create a tree. This is the last part of the proof. So how do I create a tree? So basically, I have to structure state so as a tree based on my view. So I get something we can all see, which is data 0 or E. 0 E or 0 E. 0 E is information, the unit information, and the information actually you can read information. So RW. So we have to just everything to read only. Read write is read and write. Read no write. If we want to write to it, but if we want to see what read and write, so we get the matrix 0 E row and write read write. So you do the same for the read write. So basically we create a pole. So basically for the space we have the thread we have, there's a read. So we have a shared read 0 times R. 1 R, which basically we have for me to share, we have read 0 times 2 R. So we have after EE, we got E times E equals 1 E, and then E times E times, and then that E is equal times R. E times R is RE, RE. So we have we share one epsilon state in read mode. In two read mode. So R times R is 2R. So we said 2 reads require 1 epsilon, 2 to 1 epsilon. The same for the epsilon 2 to E times 0 equals E times 0 equals 2R. So that'll be 2R. So we get 1 shared epsilon we need to encode that information. And then we do 1 times 0. 1 times 0 is 0 epsilon times right. So 2 reads equals 1 write. So 1 write. So 1 write is 2 reads per 2 reads. So if you want to write in the real world, we can write to our domain. But 1 write is EW. So 1 write over 0 is we need a write, 1 write. So 1 write is equal to 0. Equals to store this 1 write, we need 1 operation. We need 1 epsilon. EW because the write is 0 as well. 0 1 matrix. So 0 1 and then 1 0. Based on how we do it first. But E times R. So we get E times R. We get the right R times 0. So we get 1 0 and then 1 0, and this will be the right. This will be right. This will be 1. So we get 1 in here and 0 here. 1 here. So we get 1 first and then 0. So we get 1 1. So we get 1 1 because we can read, write, and skip. So we can then read and write. That's what we need really. So for all the numbers, we already got the 1 1. So if there's a 1, there's a 0, you know, but if there's a negative or something, we have to ensure the medium allows information. So we have to compute at all times 1 over 1 0, 1 or 0 in the row form, because you know the data is an array, or less 1 or 0, 1 or 0, 1 over the row 0 or 1, 0 or 1 of the row 0 or 1. 1 or 0, 0 or 1 is the row conjugate. So we get the row 1 or 0, and we get 1 1. So we get the row, we get a tuple. If it's a mutable district, what we'll say is a tuple like ordered and index. Unordered and index is a tuple. It's ordered and index. Ordered on index, but the set is unordered and unordered. So we get the set model, and this will go around. We get the vector form. Of that data structure, how that streaming function, but it can be either top down or bottom up, depending on how we process this with a stack or queue. We find it isomorphic traits we can classify as properties, which can directly be executable, which is the goal of the canonical lattice. Basically, there's a lattice and something called a folding, lattice polarity. Basically, lattice is based on movement and something called a node. So, if you want to move something in time, space, you need time. But you know, if you want to move something in time, you need space. So that's the idea. There's no consensus. You need consensus there. At the minimum, if you wanna even move a fraction of whatever unit you're in, you know. Thank you guys. So that's basically how it is. So the Cisco encoding system is literally for risk. So it's like a given private structure. It's like a space-time law structure. So this is like the IRA. So basically the data path of the IRA is the next part. So the complex structure set is this one is the risk PR, but this is what we're doing. So the complex structure that basically, if you know, listen, anything you send in time has its own equivalent in space. You know, so if you have 1,000 time, whatever the unit is, you have the equivalent of that time in space. On that space, if I have 49 squared room, 25 cube unit, 49 cube room, I get 49 times 49 times 49 time. I can do that in without being just in time room. You know, because time is a node, an edge in our domain, but the time has its own universe, its own dimension. Remember that, guys. Time is its own dimension. Space and time and their own isomorphic dimensions. Okay, guys, I love you guys. So this is what the risk does. So it doesn't really matter. But so basically, the goal is to have a universal A-star scoring. Remember, scoring is the idea, is the concept of having an algorithm isomorphic dimensions, space and time, because you know one things will never break. So that's why sparse modeling. So any data give a computer, there's an equivalent data. So there's no breaking or fragmentation. Here are the finalizing. Okay. Read. Let me see. Renew. Repair. If you can repair, if you can build it, you can break it. If you can create it, you can destroy it. So basically, for each of us and every of us in our world, after this one more time, the system part just does 15 things. If you can create something, you can destroy it. If you can make something up, you can unmake it. You know, no matter it's a fake or not, if you can make something, you can make it. If you can believe in something, you can unbelieve it. You know, whether you like it or not, that's how it works. If you fake reality, you can stay in reality, but that means you pop out your real reality. But you know, if you build it, you can break it. If you break it, you can build it, rebuild it. If you repair it, you can renew it. You know, the idea is you don't have a system of fragment fixing. You either build it or it breaks, and you build something new. That's the idea. You go to a new idea. So either you create it or you destroy it. You destroy it, you create it. You create it or you destroy it. That's the idea. There's no fragmentation in the enzyme. But you know, there's only one way to try part considered DAG that I'm trying to note as a policy. So what called TRIDENT resolution, because the engine is bound by a relation of TRIDENT. Yes, no, I'm not sure. Everything's in 3. Laid in 3s in tri models. No matter the dimension you're in. Okay. Thank you guys. Never more about the program counter, guys.